Section 18.3, conductors and insulators. So not only can charge exist on an object, but it can also move through an object. And so we say that charge can be conducted through a material. It turns out this is actually very similar to how heat can be conducted through a material. If you remember from back in chapter 13, when we talked about heat transfer through conduction, we said that there's a hotter object and there's a cooler object, and if you have a substance connecting them, like a metal bar, the heat will flow from the hotter object to the cooler object. In a very similar way, we can get electric charge to flow from the more negatively charged object to the positively charged object, because it's always going to be the electrons that are flowing towards that more positive side. So if there's a greater difference in charge, there's going to be more flow, and yeah, the two are actually very closely related. So it's a useful analogy to keep in mind that conduction by heat is similar to conduction of charge. Now, substances that readily conduct electric charge are called electrical conductors. So these are things that charge is able to move very easily through. Materials that conduct electric charge poorly are called electrical insulators. The charge doesn't get through them very well, if at all. And this is actually, again, very similar to thermal conduction, right? Where we have good conductors of heat and materials that are insulators, like an oven mitt. It's the same idea here, where charge is going to actually flow more easily, usually through metals, which are both good thermal conductors and electrical conductors. So if you have something like metal, the charge is free to move about very quickly. Insulators, they hold the charge where it's at. You may have seen on the balloon that there were some fixed positive and negative charges, and they just stayed there. They didn't move around. Or once the balloon picked up electrons, it just picked them up right where it came in contact with the sweater. It didn't move around. Turns out it's a bit different if you have a metal conductor instead of an insulator in place. So this leads us very nicely into our next section, section 18.4 of charging by contact and by induction. So we're first going to talk about charging by contact. And this imagines that we have some charged object, like our ebonite rod that we rubbed on animal fur, so that has negative charge on it. Great. Well, we can bring it and touch it to a metal sphere. And the metal sphere has no net charge initially. It's neutral. It still has positive and negative charges, but we're not going to draw them all in because we're here focused on the net charge. So when we touch the ebonite rod to the metal sphere, the electrons will flow from the rod to the sphere. The rod is transferring electrons to the metal sphere. But once these electrons, represented by the minus signs here, get on the sphere, they're like charges, and they do not want to hang out right next to each other. So if they are able to move away from each other, they are going to do that. And sure enough, that's exactly what happens. All of the electrons move as far away from the others as possible. And they stay there even after we take the rod away. We've now charged the metal sphere with this net negative charge, with all of the excess charge on the surface of the metal sphere, as far away from the others as possible. So this is one method of charging by contact. Another method is by induction. And this one is a little bit trickier. So we bring the ebonite rod close to the metal sphere, but without touching it. Notice what happens when we bring it close. When we bring the negative charges close to the sphere, it repels the naturally occurring charges, the negative ones in the metal sphere, to the far side. They don't want to be near that negative charge. And it attracts some of the positive charges, or it leaves a net positive charge, is another way to think of it, since it's the electrons that are moving. So we end up with this charge difference, where the left side is more positive than the right side that is more negative. If we very carefully attach a grounding wire while the rod is still nearby to the right side, the grounding wire connects to ground, that's to the earth, that will pull the electrons down. Electrons want to flow to the earth. The earth is a great place to dump electrons. It wants all the electrons. So we can take those electrons off, and then if we disconnect the grounding wire, remove the ebonite rod, we'll be left with a net positive charge. And once all of that's gone, the positive charges are going to want to spread out again to the very surface of the sphere. They don't want to be anywhere near each other. So this is another way of charging a bit more indirectly. That's why it's induction, not by contact itself. These are two ways to actually charge the metal sphere. There are some in-between cases, and that's if we bring the negatively charged rod close to something like plastic. With plastic, the negatively charged rod can actually induce a slight positive surface charge on the plastic. It's not enough to fully separate the charge the same way we had with the metal sphere, because plastic's a electrical insulator. So it's not able to, the electrons can't run away to the other side in the same way. But they can still shift slightly away. And this is what happened with the wall in the balloon sweater simulation, is we were able to create a slight charge separation that was enough to create an attractive force there. So this is also an important application where you can have something that is net neutral and not particularly conductive, but still can create some attraction. So this introduces conductors and insulators and the ideas of charging by both contact and induction.